I think engineering found me. I didn't find engineering. Call it engineering, call it just being curious. I've always just loved building stuff and being creative.
Welcome to the Being an Engineer podcast. Today we are honored to welcome a distinguished pioneer in the medical device arena, Chris Julian. Chris successfully led Ridge Medical Incorporated for 15 years, providing expert consulting services and contributing significantly to the medical device sector. During his career, Chris helped launch engineering efforts in over 50 med device startups and has secured more than 70 patents in cutting-edge medical technology. His extensive expertise is backed by 35 years in mechanical design engineering, including his role as a founding engineer at Intuitive Surgical, where he helped develop the instrument set for the Da Vinci surgical robot. Join us as Chris shares his invaluable insights and experiences from his remarkable career, offering unique perspectives that span the depth of medical device innovation. Chris, thank you so much for being on the show today.
Thank you, Aaron. It's a pleasure to be here and honored.
How did you decide to become an engineer? Let me preface that. You've been an engineer for, I'm guessing here, maybe 25 years, something like that. So it's been a minute.
35 years this year.
35. Okay. I wasn't, well, you wouldn't know it looking at you. I'd guess 25 tops. But so 35 years ago, or maybe closer to 40 years ago, if we're talking about college, what was it that made you decide, yep, engineering, that's what I want to do with my career?
Yeah, that's a tough question. I've thought a little bit about it. I don't know that I ever decided to be an engineer. And I have to preface this whole thing with, I don't have a formal engineering education. So maybe that decision wasn't put upon me. I just kind of dove right in and went to it. I think engineering found me. I didn't find engineering. It's just something, call it engineering, call it just being curious. I've always just loved building stuff and being creative. And so it's just a piece of me. It's not a career. It's who I am as a person. I have projects, at home, in my professional life. I've always had something I'm working on, multiple things usually, which gets me into trouble.
Well, I love that answer. And it makes me think of some of the most talented engineers that I have worked with who don't have formal training being an engineer. They never went to university, but they just kind of learned on the job as they went. And again, some of the most talented engineers I've worked with fit in that mold. Can you talk a little bit about the beginning of your career and kind of what was the path? Because I'm guessing there are probably people listening right now who maybe don't have the means to go to college, or just for whatever reason don't want to spend 4 years going to college, but really want to become an engineer. How did your path work during that time?
It's interesting. I think it's a culmination of a number of things. I live and have been living in Silicon Valley, California, my entire life. And so I think the potential of working at a startup, at a disruptor, some kind of engineering or tech company is a lot more, there's a lot more potential of that here in this location. So that's probably a piece of it. So the opportunity was kind of there. I actually went to community college for a couple of years and really struggled with math, frankly. I just couldn't pay attention, and for whatever reason, it didn't work out for me. I tried similar classes over and over, even in high school, and I struggled with it. But I still loved creating and working in science and in technology. So I took a job. My first med device job was a company called Venturetex back in '89, and they were a startup. And they were working on implantable heart restarting ICD, implantable defibrillator. And I was a tech, and I came in and I just started building equipment, test equipment, and different fixtures and jigs. And so there was an opportunity for me to kind of spread my wings and try and build things. It worked out really good. And I just naturally climbed because I was excited about it. I was passionate about it. And I've always been passionate about building things and creating things. And so that is kind of what's prompted my progress throughout my decades of work.
I think there's really something there. Nothing against college. I went to a university myself to get my degree. It was great. There's certainly a place for it. So certainly not disparaging college degrees at all. But I think there's something very valuable about the path that you took. And I know other people have taken, where you start out as a technician and you're just kind of learning the basics on the job. You're putting things together, you're assembling things, you're helping with some testing, things like that. And I almost think to myself, what better education is there than like actually doing these things, right? And learning about, okay, what kinds of designs work well, come together during assembly time versus what design elements are creating problems when it comes to manufacturing and putting assembly components together. You learn in a much more visceral way actually doing those things as a technician. So I think in one sense, spending a few years as a technician is a really incredible education and foundation for becoming an engineer. Yeah,
I think there's absolutely positives to the things you're saying. And it worked for me, and I'm certainly not going to knock a college education, and I wish I had one. So, but I've gotten by without it, and I have a skill set that's a little different than others, and I don't have, I don't even want to call it the burden of education, but there are particular things about mechanical engineering, and I'm a mechanical engineer, designer, I call myself. There are things about the mechanical engineering field that really are hands-on. And of course, like with many things in life, it's a balance. You need to understand the basics, and the math and the science behind what you're working on and the materials you're working with and the processes you're working with. But you also, on the flip side, get a great understanding when you're there working with your hands and actually doing. So the experience piece of it has been huge for me, obviously. Fortunately, I've worked in a gazillion startups, and every one of them has very well-educated engineers and people that I could rub elbows with and learn from. And so observation and being curious has been kind of my schooling, I guess, if you will, and just trying to understand the pieces that I'm missing and how I can, progress and do better and learn so I can take on bigger projects and get the respect that's required to drop into those positions that allow me to do the really important work.
So thinking back over your career, 35 years at this point, a lot of which has been in startup environments where, to me, the startup world that's the most challenging engineering, because you're solving those early problems, right? It's not so much okay, you've got a product, it's in manufacturing, let's make some tweaks and refine the process, but you're figuring out what the process is. You're defining the geometries, the mechanisms, all those things. Can you think of an experience where you faced a pretty significant challenge and how you managed to overcome it? I think I'll refer more to like a technical challenge rather than a communication or interpersonal challenge, if anything comes to mind.
Yeah, I don't know that any particular thing comes to mind. I mean, every project you work on has challenges and things that you maybe don't understand. It's not always about just running through this algorithm and out pops a product. There's a lot of different pieces, and it depends on the product, of course. Earlier in my career, I worked on primarily mechanical objects and devices. As we roll into 21st century with electronics and software and robots, things are a lot more multidisciplinary in that respect as far as engineering roles go. So it's harder today than it was, say, 20 years ago. But I think just being curious, trying to find solutions, leaning on people that really know what they're doing as well, and being a good teammate, because there are many times when I don't know how to run a calculation or how to perform a test, and I'll lean on my teammate, and he'll teach me or she'll teach me, and vice versa. So, I'm in the machine shop teaching people how to run the equipment. There's so many ways you can kind of help and lean on each other and have that union, that team that really is the joy of engineering in a company is having a team to work with and build, world-class products with. It's not just one person. It never is. So.
Yeah, I think that I like that you use the word joy. That's a big word for me. And I think joy comes from doing hard things with people you care about. So that the team aspect is super important. You also mentioned multidisciplinary approaches, and I agree. I've seen that become much more important over the past decade or so. I have a pretty limited skill set when it comes to engineering myself. I'm very strong mechanically, but electrical is my Achilles heel. That's I guess my analog of your math. I never understood it for whatever reason. Electrical, I don't do it. It doesn't make sense for me. To this day, I get ribbed by my team. Don't let Aaron near the electrical. Don't have Aaron help you with wiring.
Let the magic smoke out.
Exactly. You'll see the magic smoke if I start messing with your electrical for sure. But some of the younger engineers that I work with, I am so impressed with them because they come out of school as a mechanical engineer, don't necessarily have any direct experience with electrical or with programming, but especially for what we do, where the variety of projects is so vast, we'll get a project and it will require a little bit of programming or some electrical work, and they'll just figure it out and do it, And I think that's one of the hallmarks of a good engineer is not necessarily that they know everything at the moment, but they have the ability to learn it.
Yeah, I totally agree. And I think being open-minded with learning new things and being curious and passionate about that growth as well, sharpening the saw, if you will, is super important. And that really is going to define how successful you are, I think. As far as younger engineers, newer engineers, I think inherently there's just a lot more electrical and software based programs and components and systems that are a piece of mechanical engineering. So it is something that comes as a bonus, I guess, if you will, with a mechanical engineer. And that wasn't necessarily the case, a couple decades ago. So times have changed. And I think, it's really kind of interesting. I was thinking recently about how I've really focused on robotic surgery in the last couple decades. And it kind of has come full circle as far as this mechanical mechanism, kind of these old world types of mechanisms that we use to solve these problems. And with robotics, mechanical engineering is front and center. And there hasn't been, I think, a lot of technical products in the last couple decades that really have leaned on mechanical engineering as much as robotic surgery and robotics has recently. So it's almost like this resurgence of mechanical design, which I think is neat because it felt like it was kind of a lost art at some point. I mean, you used to build an actuator out of a motor, a lead screw, and a nut and a carriage. Now you just buy it, and you program it. So there's all these subsystems now that you can buy and just drop in. So it's not really the same. I mean, it's great, but you can't always adapt these components into kind of an integrated system as easily as you could before, because you were already forced to design a lot of those subsystems.
Yeah. You've talked about, as far as skills that are important for engineers to have these days, right? We've got multidisciplinary functions, we've got software, we've got electrical, of course, there's mechanical. You've talked about the importance of being curious, right? Just wanting to learn new things. Anything else come to mind as far as attributes or behaviors or habits or foundational skill sets that are very critical to engineers these days?
Yeah, I could speak a little bit to kind of bioengineering or, human, anytime you're dealing with the human anatomy, procedures, whether it's surgeries or clinical procedures, there's a number of things that go with that. And really a lot of the work I've done over the course of my career has been procedural development, not just device development. So they kind of go hand in hand. And when you start thinking about and talking about procedures, you're talking about workflow, you're talking about human factors. You really kind of need to look to the end to see really what the outcome or what you're trying to accomplish. And it's not always to develop a device. It's really to solve a problem surgically or clinically. And so the device is just one little piece of it. So it's a broader picture, I think. But yeah, I think a lot of the things that I believe has brought me success has been having a perspective of everyone on the team. The perspective of the different engineers. I'm not a big electrical guy like you're suggesting you may not be. I'm not a big software guy, but I kind of understand what they need from me as I design the mechanical components. They need to have a motor. They need to have a sensor. They need a power supply somewhere. And so where do you package it? Where's the right place to monitor this torque? Is it at the distal end or the proximal end? Understanding kind of those perspectives of what they're looking for. In medical device industry, you have this huge regulatory piece, where you need to have efficacy and safety, primarily. And so what does the regulatory person want to see? And how are you going to prove that through testing? How are you going to prove that it's safe? Are you going to do bench tests? Are you going to do, other types of clinical testing and ultimately first in humans? How do you perform those tests? Those studies? What's the output? So you need to understand the regulatory piece. Quality manufacturing is a big piece of design. If you want to sell your product and actually make money off of it someday, you could have the greatest thing, this greatest tech, but if you can't make money off of it, the world is not going to have access to it. So the company will not survive. So it really is important to be thinking about, the viability of your design and whether it can actually make enough money to justify its existence and its build up and design.
Let's talk a little bit about DFX, right? Design for manufacturing, design for assembly. These are big topics that could consume an entire episode or much, much more by themselves. But when you're starting a new design, what thoughts do you have kind of projecting into the future about design for manufacturing, design for assembly that you're very cognizant about in the very beginning of your design?
So I agree with you 100% that DFX design for assembly, design for all these different pieces, manufacturability ultimately, are super important. And again, if you want to have a viable product, you really, again, need to be looking to the end. You need to understand how your device is ultimately going to be manufactured, constructed, fabricated, assembled. the sequencing of assembly, whether you're going to need a whole flock of fixtures and jigs to build it, what kind of technical skills your assemblers are going to need if there's going to be humans putting this thing together. There's just so many pieces to it. And it's something that really, I strongly believe that is defined, the manufacturability of a particular product is defined earlier rather than later. The architecture of your product is a function of really, it should be like how it's going to go together, how you're going to manufacture the individual components. Are these going to be molded parts? Are they going to be machined parts? We have all these shortcut tools now where we can iterate very quickly. We have 3D printing. What you don't get with 3D printing is understanding really the process of machining a part, the process of putting things together. Sometimes the challenges of undercuts and other features that might be embedded in that 3D printed part that you cannot have in an actual molded part. The pulls and undercuts, it just makes it challenging. So, understanding, the processes, the materials, that are going to go into those processes, all of those are super important. And they really need to be thought about at the get-go, right at the start, when you start thinking about, how is this thing going to come together? What are the components that are inside of this piece going to look like? And, even something as simple as hardware to put it together. I used to laugh when I was younger because I'd hear these seasoned mechanical engineers say, we want to have all the screws to be identical. I mean, we don't want to have a bucket of 100 screws and they all need to be identical. And I always thought, well, that's kind of silly. Why can't we have 3 different types of screws? And then you go out on an assembly line and you watch what happens when you have a multitude of hardware, especially if they're kind of similar, different lengths, maybe same screw size, different length. They get mixed up, and then all of a sudden you've got a short screw in a long thread that's going to pull out really easily or strip, or you've got a long screw that they just screwed halfway in and they have to back it out now, wasting time and changing things. And so little things like that, they really make a difference. And I think in Silicon Valley with startups, we don't tend to think a lot about those types of things. We usually build something and then we put a bow on it and we sell it off to one of these big companies. And then they inherently productionize it, if you will. So I think there's important pieces to understanding what this thing's going to look like when it's done and how you're going to get through along the way.
Yeah, there's an engineer on our team who at a previous company worked on the design of a device that had been designed by someone else, a different group. He inherited it, and this other group had demonstrated that it worked, and it worked well. And this blows me away because the company was not a small company. It was a large, mature manufacturing company, and they had this device that had never been tested in actual parts. I mean, like molded parts. All they had done was 3D print everything and test it. And the 3D printed parts didn't have any draft on it. They didn't have appropriate considerations for, undercuts and shutoffs and things like that. And so, everything worked great with non-manufacturable parts. And once they started putting the draft on and undercuts and things like that, then all of a sudden, it doesn't work. And they spent millions of dollars trying to make this, trying to fix it. And I think ultimately they finally got to a solution that worked, but it cost them so much more money and so much more time than it would have had they thought about the DFX in the beginning, right? And even if it was 3D printed parts, put the draft on it. Make sure that your geometries are identical to what they're going to be in final production processes.
Yeah, I think I've seen that many times as well. Small companies I haven't spent a lot of time in larger companies, but it's a great segue into failure to fail fast, because that's really what you're doing when you're 3D printing, right? You're trying to get as many shots on goal that you can in a specific amount of time. And so every product development cycle is as short as possible, right? They're never long enough. But if you can cycle or design spin in a week versus a month, think of how many more design spins you've got, how many more shots on goal you actually have to get that product right. And, the fail early, fail fast, the word fail, I think there's just obviously a negative connotation there, but that's part of our job. And it's not even a fail. This is how you learn. You build something, you test it, you learn pretty quickly it doesn't work, and you iterate. And so that is unfortunately is kind of the method in human medical device development. And I say that it's different than, say, building an airplane. I mean, if you were building an airplane, you can do a lot of it theoretically on CAD, model it out, do all the calcs. That's a little different. But when you start talking about the human body, every one of us is different. Our tissues are different. The size of us are different. Everything, the structures inside of us, every human being is different. And so to get a particular device design that is workable across all of our bodies is not always easy. And we're not dealing with hard metal, rigid structures. We're dealing with viscoelastic, fluid membranes. And so how they react when you squeeze them or compress them or interact with them is really interesting and challenging. I remember back in the early days of one of the companies I worked for, one of my coworkers was trying to develop a scalpel, right? A miniature scalpel. And you could probably figure out what that was for, but it was super interesting to me that no matter how sharp that scalpel was, you could not cut tissue. And it turns out that you've got to have counter traction with that cutting action to kind of allow the tissue to stop or to be held in place or be stable as you cut through it. It's kind of like, and this is a quote I heard from another engineer years later. It's kind of like cutting a steak without a fork. I mean, you put the knife on the steak and it just slides around. And until you lock down the steak for that counter traction, you can't really cut through it. So probably a bad analogy, but it's different with medical devices. And I think that's where, and maybe this is full circle back to your first question about how I ended up where I ended up in the medical device industry and in startup industry and in Silicon Valley. There's a unique requirement for people that are just good at iterating and good at empirically testing things. And so throughout my younger years, that's what I did. I just went out and built stuff. Didn't know what I was doing, but figured it out, time and time again. So that's a really interesting piece about medical devices, because you don't know really what the solution is going to be. It's hard to predict.
Yeah, that's R&D, which is what I love, the early stuff. And
you cycle through the failures, and the sooner, the better. The other piece about fail early, fail fast, I learned this from another engineer, actually probably just less than 10 years ago. And it was a really simple comment that he had made in one of the meetings. And he said, why don't you decouple these two little pieces and test them and build them and develop them independently of each other? And then, just make sure you guys are talking to each other so you can marry it together later. But I took that and I use decouple as a pretty important word in my engineering vocabulary these days, because it allows you, especially in a multidisciplinary environment, to kind of break away from your peers or your other team members and let them do their work, you do your work. So decoupling things as much as possible within reason is always made sense to me. And I don't hear enough of that in the industry. And so I don't know if it's just me or my perspective of it, but breaking things apart, simplifying things, taking it to the basic need seems to really improve cycle time and complexity and confusion.
I could not agree more. I think that is one of the foundational principles of engineering and R&D and product development. In fact, I had an experience not too long ago, a year or two ago, kind of engineering adjacent, maybe I'd say. At work, I had purchased this camera system. It was this really cool jib arm, and there were motors on it, like 3 or 4 different axes, in order to get some really nice video of products that we've developed, right? So I'm taking like these nice swooping cinematic videos showing the products that we've developed for our marketing. And like I mentioned, there were 3 or 4 different axes of motion on this, and they all work together via an app, and it's super easy to program the motion on this. So I put it all together as I unboxed everything. I was super excited to start using it, and it wasn't working right. You know, I'd program it to start at point A, move to point B, and then come back to point A. And I noticed that it would start at A, it would go to B, but it wouldn't quite come back to A again. It would be just a little bit off, but far enough off that you could tell for what I was trying to do, and it didn't work. And I spent, it's really embarrassing to say this now, I probably spent like 4 hours trying to troubleshoot this, 3 or 4 hours trying to troubleshoot it, could not figure it out. Finally realized, oh, dummy, decouple all of these different axes and just test one at a time to figure out where the problem is. So that's what I did. And it was very clear, very quickly, what was not working. Turns out one of the axes was not, it was damaged. It just didn't work correctly from the factory. And then another one, I was using an incompatible camera lens. But these problems became apparent so quickly when I decoupled everything and just tested the constituent components as opposed to trying to troubleshoot the system as a whole. So that's an example from like a mechanical system, but the analogy that you had is awesome, where instead of a mechanical system, you're talking about like a development team and these different disciplines that ultimately all have to come together in a system, but you silo them in a productive way and have them just do their thing, right? So you know that their part works, and then when you bring them together, if the thing as a whole doesn't work, you can go back and say, okay, well, where were we seeing individual failures within the different disciplines?
Yeah, I think that's right, and I think it probably is more prominent these days because of these really complicated systems that we work on, right? I mean, like you said, you had multi-axis system that you probably wouldn't have had, a decade or 2 decades ago, right? So, it is interesting how we break things apart.
Yeah. Well, let me take a very short break here and share with the listeners that our company, Pipeline Design and Engineering, develops new and innovative manufacturing processes for complex products, then implements them into manual fixtures or fully automated machines to dramatically reduce production costs and improve production yields for OEMs. And today we have the privilege of speaking with Chris Julian. So, Chris, something that I've been thinking about a lot, especially as a business owner at an engineering company, is that as engineers, I think we'd all love to simply work on the engineering projects that we find interesting and do so to our heart's content. But the reality of engineering is that most of us work at companies with business objectives that need to be supported by our engineering efforts. How do you think about the design engineer's role relative to the enterprise as a whole?
in what manner? In developing a product or in working within a business structure or a company? Because I've got opinions on all of them.
Let's start with developing a product. As engineers, we can get distracted by chasing a rabbit down a hole, right?
So really about focus and about priorities, I guess it sounds like, right? So yeah, I mean, it's always challenging. And I think there's more of a personal challenge there than maybe even a career challenge, because we all have things in our life that we don't want to be doing, and we need to learn and teach ourselves how to accomplish those things that aren't as fun. And so that is probably more of a personal challenge than a career challenge. It is interesting. How do you talk yourself into doing something, or how do you just dive in? I think probably everyone's a little bit different. For me, I work super hard to try not to get into situations where I'm doing work I don't want to do. I guess is the short answer. Do your job really good, and hopefully you'll get the good jobs. No, I think, that is one of the stark realities, I think, that a lot of new college grads discover when they come into these startups and these companies, primarily probably bigger companies, actually, that the real design work is, and maybe I shouldn't even say this out loud, but it's 10 or 20%, right?
Oh, now they all know.
Yeah, I know. I'm going to change professions. So I think that is it's tough, right? Because you can only be you can only create so many things, before it's time to test it and prove it and simplify it and do all these other things and all the paperwork, unfortunately, that goes along with it, especially in the FDA regulated, in the healthcare system, where you can't just kick out products without having, a lot of paperwork, and it for good reason, right? Understanding the pedigree of something, understanding the design history of why it was, built the way it was, and all the testing around, the product to prove that it's going to be safe.
I think of a friend of mine who has this phrase called real good versus feel good. And there was I remember a few years ago, I was putting together a spreadsheet, and I chased a rabbit down a hole. I thought to myself, oh, it'd be really cool if this spreadsheet would have this feature, and all the user has to do is like click this button and all these things happen.
Save the world with your spreadsheet. Right?
Exactly. Right. Yeah. Exactly. So I probably spent half a day building this spreadsheet, and it was beautiful at the end. It worked exactly the way I wanted it to work. And it gave you this very visual display of data that had been entered. And I thought, wow, I'm really proud of myself for putting this together. And that lasted for about a week or two until I realized, you know what, I actually haven't really used this at all. Like it was fun, and it looks cool, but it has not helped me do my job any better. So that to me was a feel good project and not a real good project.
Well, it was probably a lesson for yourself, right? I mean, it sounds like you taught yourself a lesson, and so
that's
you
true.
got something good out of it, right?
I got something out of it.
Probably new skills, and maybe someday you'll end up with something like that required. But I think it is interesting how we can really struggle doing something that we don't want to do, and a lot of it is mindset. And this, and I don't know how much we want to delve into kind of this Buddhist philosophy thing.
Go for it. I love it. Love this. Let's hear all about it.
But no, I think being in the moment, mindfulness is the big thing now, right? But there's a lot to it. If you can get out of your head and just do the work will just go by. And so understanding when you're fighting something, mentally versus, just getting the work done, or even flipping the story, and creating something good or some additional piece out of it. that's gonna make it a little bit easier to follow through and finish it. And it gets easier, I think, over time. The more you do these jobs that you maybe don't want to be doing, I think also there's an inherent joy in just being immersed in this kind of work. At least there is for me. I mean, I sometimes, I have to pinch myself and remind myself that I am getting paid for this. And then there's other times where I have to tell myself, you know what, tomorrow will be better, or in a couple moments it'll be better, or whatever it is, because, these feelings are very fleeting, whether they're good or bad. So you can get past them pretty quickly.
Let's talk a little bit about continuing education as an engineer. There's always something else that we can learn. What has been your approach to continuous learning and development? Do you have any strategies or principles that you follow, and how has that impacted your career?
Yeah, that's a good one, and very relevant. I mean, for our lifetime, really. I mean, things are just evolving so quickly, and they say that they're just going to pick up speed even more. So you really, you have to, if you want to keep your head above water, you've got to keep up, with understanding all these new apps and all these new systems. So they're on some level, I wouldn't say forced upon you, but they're in your direct line of sight if you want to develop products. It's just inherent in the world and the companies we work in nowadays. So as far as seeking other types of things that I want to learn, or educational, and educational is kind of a bad word, right? I mean, it sounds like work, right? So it doesn't have to be work. There's always things we can be doing that are going to improve our ability to design better products. And so I think if you can flip it on its head that way and just know that if I can figure out how to program an Arduino board and then trigger this motor and these sensors and control the output of this particular device instead of a couple switches or potentiometers per se, it's going to be more elegant. It's going to be just a better device all around and more modern. So there's all kinds of reasons to be doing it. I guess, I try to find a good reason to do that work and to find those new lessons and those new things I want to learn about. It's tough. I mean, we dive into these projects and sometimes we don't come up for a year. I mean, it feels like we just lost a year because we're just head into it, and there are schedules to be met, and not that it's bad. I mean, I think it's probably good when you can just kind of lose yourself, and the next thing you know, it's 5 or 6 o'clock and your day's done. It's like, wow.
Time flies when you love what you're doing.
Yeah, it really does. I mean, that's the overarching probably story or comment I want to make is that love your job. Figure out what you really enjoy doing and try to find a way to make money at it. It's I love engineering. I love being creative. I love watching something go from a list of design requirements to an actual product. It's really it's so rewarding. And I think certainly for me, as I get more on in my years in my career, it's not just proving that you can build one thing. It's bringing it to the masses. It's developing it so you can manufacture it inexpensively. So not only does it make its way out into the world, but it stays there for a little while before someone else replaces it with a cheaper version per se. So there's all kinds of challenges, I think. And my challenges in the last few years have been more about the manufacturability piece of things. Like, how do I make this thing so inexpensive, still quality, but so inexpensive that it's not going to get replaced, It still does what it needs to do. And you can make millions of these things, it's just more rewarding, I guess, than just building one prototype, but you have to start somewhere.
Yeah. Can you think of a specific experience, a story almost, where you had a part and you needed to make it less expensive to make? And with as much detail as you can share, of course, what did you do? What did you change in order to make it more manufacturable?
I think that's a great question, because it leads into understanding materials and processes. And I think if you really want to be a good device designer, knowing all the different ways that you can shape a part or create a part, whether you're coining it, molding it, metal injection molding it, sunless grinding it, all these different methods of manufacturing it. If you understand the whole gamut of what's available to you, and then you take all the different materials that may come to be in your product, and medical devices, there are a lot of engineering polymers, there's a lot of more exotic metals. But if you understand how they behave, are they springy? Are they brittle? Can they easily be molded or coined? What are the tolerances around this process versus this other process, and then the costs associated. So if you costs associated with those particular processes, if you can get a good handle on what's available to you as far as how to fabricate things or construct things, what's available to you for materials, understand the costs, understand the tolerances, and even understand the lead times to get those parts, because that goes to the design spin that we talked about earlier. You can really have a broad selection of options when you start to take cost out of things. And so that's where you kind of need to start. And then you start thinking about a design for something. And I know that if I'm working on something that it's like a endoluminal product or something, and it's got a bunch of links, kind of vertebrae, if you will, a spine to it. And each one of those things is an individual component, and you've got 50 of them. You can't be charging or paying $5 per link. I mean, it would have to be like 50 cents or 5 cents. So what are the construction processes or techniques that would meet kind of that time or that dollar constraint? And then what are the tolerances and the strengths and things like that? So I think in a backwards way of answering that, I think understanding, the costs that are tied to your particular design to make it viable and survive out in the world and even be a product someday, because it's not so expensive. Understanding that stuff early on helps you define what those little links might look like, if you will.
Yeah. Yeah.
I don't even know if that answered anything, but it's probably just rambling a bunch.
No, injection molding, right, comes to mind for me. You want to make 5-cent parts and a lot of them.
And they've got to be small too, maybe, right? And
right.
And miniature micro molding has come a long way in the last 20 years. It really has. But how you mold it, or do you stamp it? Do you coin it? Do you metal injection mold it? I mean, they've got printable metal injection molded parts now that are literally 3D printed and then sintered. So there's so many different options. Electrochemical etching was always a fun one. That was great. You could create a piece of artwork, a digital DXF file, and you could iterate your part 100 times on one build lot. So you didn't have to machine 100 different parts. You would chemical etch, one sheet with 100 different embodiments on it, and it would give you all these different options kind of for free. So all these little tricks that you can deploy as you try to fail early, fail fast, and spin your cycle as quick as possible.
Yeah. Well, we talked about loving what you do briefly a little while ago. And you have this hobby car that you have put together. I would love to hear a little more about that. I think I could be wrong. I think that it even won some kind of award, like a best in show competition award, I think is what I saw. But
yeah, this is a European kit car that I lusted over a couple of decades ago, actually. And I finally got up the nerve to buy the kit. It came from a small little boutique kit car company in England called Ultima Sports. And it was an Ultima GTR that I bought, 2006. It was a kit. It was a well put together kit, fiberglass body that was gel coated. The color was already there. I didn't have to worry about painting it later. A lot of expense in that. But yeah, I've always just loved building things and being creative. And so I took this car that was already a really nice piece of equipment, piece of machinery, and I pretty much modified every part that went into it. And so, put my special touch to it, lightened it, whatever, made different brackets. But yeah, it's just another one of those projects that I'm always kind of toying with or thinking about. But yeah, it took a good 15 years to get that on the road. And I guess I would say I'm the builder and not the driver. So, more the engineer and the creative side of it. It is fun to drive, but really the thrill was building it and designing it. So I did a lot of the work in CAD, which was a great tool. It saved me a lot of money and a lot of time, designing things on the computer rather than actually going out and fabricating them. I 3D printed a lot of parts. I did scaled models of the thing. Actually got, I don't know if we've got video
wow.
here, but there's a 10th scale model of the chassis. So
that's awesome.
Yeah, it's a fun, I don't know, keeps me off the streets, I guess. But no, I went to a show in Pacific Grove during Monterey Car Week, which I go with my boys every year, and entered it in the Pacific Grove auto rally, and won Best in Show in 2022. So that was pretty cool. I think there was 300 cars. And it wasn't certainly Pebble Beach or something like that, but yeah, it was great. And it was nice, to have that validation, I guess. You never really know, I guess, how well you do anything until other people respond to it or something. I don't know, but it's been a blast. It's still, it's on jack stands about 50% of its life. There's always some new modification.
So it's still a work in progress at this point, still tinkering with it.
Always.
Always.
Yeah. I'm fortunate enough to have the money to be able to do that. And I do a lot of the work myself. So it's not a horrendous, you don't pay for labor. I am the mechanic.
Yeah.
And I learn new skills every time there's something new to do. I mean, I designed a whole set of headers for that thing. And so that was interesting. And so when you talk about, education, that's kind of how I see it. It's like, how do I want to expand my capabilities?
Well, maybe let's end with, one last question here. And I think we've already kind of covered some topics in this area, but I'll be a little more direct in how I phrase this question. What is one thing that you have done to accelerate the speed of engineering?
One thing I've done, I think it's tried to enable others around me to kind of mimic some of my little shortcuts and tricks and things that I do. A lot that we spoke about here, the fail early, the fail fast. Always, sense of urgency is something that comes natural to me. And maybe it's a component of the joy that I get and the passion that I have around this, but just trying to have a sense of urgency, and that I think maybe inspires others. I'm hoping, instead of upsetting them. But I think just trying trying to help the team and bring people up to speed, mentor recently, more often than not. But no, I think it's probably helping fellow engineers.
That is the role of a more seasoned engineer, isn't it? It's still doing the work, of course, but it's growing into that mentor role where you can enable others to do the work quickly and efficiently, as opposed to just doing the work by yourself.
Yeah, I think it's a curious thing. I was told a while back, there's kind of 4 quadrants of your career. There's the learning, earning, mentoring, and the legacy quadrants. And so I would like to think that I'm in kind of the mentoring, kind of giving back, You go to school, you learn, and then you earn your money and you get a foothold in your life and, start a family or something. And then you give back. And then ultimately in the end, I guess I don't know what you do with legacy, but I better figure it out soon, I guess. So,
that's the next step. Yeah.
Yeah. I think like what you said is, my experience again with new grads is they don't always have a lot of the hands-on and a lot of even the startup kind of experience. And big companies are different than smaller companies in the sense that you get pigeonholed is kind of a strong word, but you can easily kind of get cornered into an area that doesn't give you a lot of broad exposure to the overall engineering process, the development process. And so I would suggest or certainly try to help people to kind of expand the horizons in that respect.
Love it. Well, Chris, is there anything else that you think we should talk about, or anything else that you'd like to say to the engineers who are listening to this that we haven't covered already?
No, I think we covered it pretty well. I really appreciate being on the podcast. It is kind of nerve-wracking. I'm not a big I'm a solo contributor, I guess. And so I've never been like the big, public speaker. So it's interesting that way, but I do appreciate you having me on.
Absolutely. Thank you for being willing to do this. You talk about mentoring, and this is a chance. I mean, effectively, you're mentoring hundreds or even thousands of people who are downloading this episode and listening to it. So thank you for contributing to that content within the engineering community. And for those who are listening, probably some of them are going to have questions for you. If they do have questions, how can people get in touch with you?
Yeah, I think the best way is through LinkedIn. I mean, I think that is our forum these days.
Yeah,
right?
Yeah, it is.
Unfortunately, it's kind of the standardized forum for us, all of the career-minded people to kind of meet. And so that would be a place to find me and message me.
Wonderful. Chris Julian. Well, thank you again so much for being on the show, Chris.
Thank you. Appreciate it.
I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.